There are many problems in the section that we're going to do today, which is released questions 81 through 90. And many of these questions are going to be questions that involve calculations or balancing of equations, also stoichiometric type problems. So we're going to get started with this guy, which is ammonia plus oxygen going to nitrogen and water. Now, to balance this guy, I want to point out something before we begin. We've got an even oxygen here and an odd oxygen, meaning in the molecule, they're even and odd. Odd can be made even, but even can't be made odd no matter what the coefficients are. Okay, so that's one thing that we have to keep in mind. The other thing is that here in the ammonia molecule, we've got an odd number of ammonias, and over here, our odd number of hydrogens, I'm sorry, and over here in water, we've got an even. So we have some odd even issues. And one of the ways that I like to start is to take the subscript of this atom and put it over as the coefficient here for ammonia on the left-hand side. Oops, not 3, 2. Now, the subscript of this hydrogen is going to become the coefficient over here. And what did that do? That gave us 3 times 2 hydrogens on the right, which is 6. And on the left side, it gave us 2 times 3 hydrogens on the left, which is 6 hydrogens. So our hydrogens are balanced. And one other benefit that we got out of this one, this coefficient of 2 needs to, or is going to balance the coefficient of the nitrogen, which at this point is just 1. Now, what we've just done is we have gotten in balance the nitrogens and the hydrogens. So nitrogens and hydrogens are balanced. And anything that we do in terms of changing coefficients, like if I doubled this 3, I would have to double the nitrogen, and I'd also have to double the ammonia. And so what I want to do, because I have an issue now, I can't balance this equation unless I have an even number of oxygens, because the oxygen on the left is an even number. So what I plan to do is completely cross out this guy and double him, so I will get an even number. But because my hydrogens and nitrogens are balanced, everything that has hydrogen or nitrogen in it has to be doubled as well. Nitrogen at this point in time, which sits right here, has no coefficient, so when I multiply this by 2, it's just 2. When I multiply this guy by 2, it becomes a 4. And now I look and see how many oxygens do I have on the right side of this equation. And this isn't a 2, this is a 6. It's 2 times the 3. And so if the 6 has a coefficient for water, I have 6 oxygens. So over on the left side where I have my O2, I can put a 3 here, and that will give me 3 times 2 oxygens, which is 6. Now in the question, they want the coefficient of ammonia. And so the coefficient of ammonia, that's what they asked for, is sitting right here. And we're done. Question number 2 here is another calculation problem. And we're starting out with carbon 12. That's what's given in the question. Carbon 12, right here. So if they're telling me that I have exactly 6 grams of carbon 12, that's going to be my given in this problem. And so I've written that right here. Now we have to decide what to do next. We're looking for moles. So moles of carbon 12, 12 stands for the mass of carbon. So if we're talking about carbon-12, which we are, the grams are going to be 12. Now, what do I want on the bottom of my next fraction? I want to be able to cross out this grams of carbon, and so grams of carbon is what's going to come down here, and the molar mass is 12. So 12 grams of carbon is 1 mole. That's the ratio of moles to grams for carbon-12. And now, as you can see, what I'm going to wind up doing here is canceling out my grams, and so I wind up with moles, which is what I'm looking for, and moles is just going to be 6, my starting number, divided by 12, which is the molar mass, and that's going to be 0.5 moles of carbon-12. That's all there is to that one. Here we are with another calculation problem, and we're going to wind up having to change grams into molecules. And to do that, we're going to take grams and go to moles, and then we're going to put that into atoms, not molecules, atoms. And all of this has to do with platinum. Now, I tell my classes that to get from grams to mole, we use the periodic chart, the molar mass of whatever it is we have. If it's an atom, it's the molar mass of the atom. If it's a molecule, it's the molar mass of a molecule. Once we get to moles, we're going to get to atoms by using what I call AVO. AVO is that nice, big, huge number, 6.02 times 10 to the 23rd. Okay? So 6.02 times 10 to the 23rd is what we'll use there at the end. Now, to do this problem, we have to start with a given. Givens are always over 1. 96 grams, 97.6, sorry, grams of platinum over 1. Next, we're going to get the molar mass. Molar mass for platinum is 195 grams. So what are we going to do with that? So molar mass, 195 grams. The 195 has to go down below. And this is grams of platinum. Why does it have to go down below? So it will cancel with the grams up here. And 1 mole is at the top, and that's also platinum. The next thing we need to do, this is our third fraction, and then we're done, is use the AVO number. Now the AVO number is going to be how many grams are, how many pieces, which will be atoms or molecules, in this case atoms, and the number of pieces that are going to equal 1 mole. So I put my mole on the bottom. 1 mole is going to be on the bottom, so I can cancel moles here. And this, of course, is platinum. And 6.02 times 10 to the 23rd is up here, and that's my atoms of platinum. And I've done my entire calculation. Now all I need to do is realize that my 195 here, this guy, is 2 times this 97.6. When you divide 97.6 into 195, you get 2. So if I simplify this guy, well, I'm going to rewrite it here while I take a pause. So now you'll see that this number, when it cancels out with this number here, cancels with this one to give a 2 down here, because I divide them both by 97.6. And so we have 2 on the bottom. When we divide the 2 here into this number, we get 3.01. And that's all that's left. Everything else is canceled out times 10 to the 23rd. And so we see the answer here is going to be, of course, letter D. Now in this problem, I've already underlined and circled for you. And let's take a look at what I've done. Right here, I'm pointing out that equation is absolutely essential. This is what we call stoichiometry, using a balanced equation to do a calculation. So we're starting out with 1 mole of methane. I choose to use the 1 mole of methane rather than the 2 moles of the oxygen because it's an easier number to work with, so why not? All I need to do is look at the balanced equation. I will start out with 1 mole of O2 over 1. That's my given. Now, the next thing I need to do is look at the balanced equation. Because I'm already in moles, I don't need to calculate grams here at all. It makes our problem a whole lot easier. So if I have a mole of oxygen, how many moles of, let's see, in letter D, this is our correct answer, and I'm just going to explain why this answer works. My first job is to do the mole ratio going to water. When I go to molecules of water, I'm going to find out that the molecules of water are, oops, changed my mind, decided to use methane instead of oxygen. Okay, and what I've done down here is I've underlined, as you can see, the molecules of CO2, which I have to calculate first and see if those come out right. And so how are we going to do that? We have to use the mole ratio, which happens in this fraction right here. Going back up to the equation, you can see the mole ratio of CO2 and methane are 1 to 1, okay, because there's no coefficients there. So down here in this fraction, I am going to use a 1 to 1 ratio. That gets me from moles of CH4 to moles of then CO2. And the next part is to get us into molecules of CO2, and this is the AVO number. The AVO number, 6.02 times 10 to the 23rd, is equal to 1 mole of CO2. And so you can see that that does work. We come up with 6.02 times 10 to the 23rd CO2s. So there's no problem here. Now, the next part is to figure out if we have 1.2 molecules of water. Now, what I've done is I have circled the mole ratio of water to methane, and you can see that's a 1 to 2 relationship. Because that's a 1 to 2 relationship, and I'm going to again start out with 1 mole of CH4, the 1 mole of CH4 is equal to 2 moles of the water. That's the mole ratio from the balanced equation. And the last thing we need to do is put in the AVO number, because moles will be on the bottom, and we will have AVO number at the top, 6.02 times 10 to the 23rd, and this of course is going to be for water, in both cases, top and bottom. What we wind up with is 2 times 6.02, and 2 times 6.02 is going to be 12, but we're going to wind up with a little problem there because that moves the decimal. And I'll work that out for you and show you that in just a sec. Okay, those numbers are now in front of you, and you can see what I did here. I'm just multiplying by 2 because this 2 is going to be multiplied by the 6.02, but we will still have a factor of 10 to the 23rd. See, moles here cancel, moles of water cancel, moles of methane cancel, and all we're left with is the numbers that you see that I underlined right here first. So this is going to be 12.04 times 10 to the minus 23, but we have to get that back in scientific notation to match what they gave us as a possible answer right here. And that was 1.2 times 10 to the 24th molecules, and that is exactly what we come out with. Why is that? Because we move our decimal over here, we need one more power of 10 up here to get that back to where it belongs. All right, we need one more positive to move it back. And our net result right here is the other answer that we wanted, and that's why letter D is the correct answer. In this problem, they want to know the moles of methane that are contained in 96 grams of methane. And to do that, we have to know what the molar mass is. So the first thing we want to do is add up 1 carbon and 4 hydrogens, and we come out with a total mass, taking all these numbers from the periodic table. Because 4 hydrogens at a mass of 1 each are going to be 4, and 1 carbon at a mass of 12 is, of course, equal to 12. So we add those up, and that's the molar mass of methane. Now we're going to have a problem that is going to require us to do a calculation, and the way we're going to run that is right here. Okay, we're going to start out with our given amount of methane, which is 96 grams, right there. And that methane has to then be, see, this is the given over 1, the way we always start these calculations. And the next part is the molar mass, which we calculated up top there. And the molar mass here is going to be 16 grams is equal to 1 mole. And because we are wanting to cancel the grams out, which I've already crossed out, you can see that the grams cancel and we're left with moles of methane on the top. And when we divide the 96 by the 16, we wind up with a total of 6 moles of methane. Okay, in this problem, they're asking how many atoms are in chromium sample with a mass of 13 grams. So first of all, you want to outline for yourself, see what you're supposed to do. We've got to get chromium grams to moles of chromium. That's going to happen with the molar mass from the periodic table. And then you need to change your chromium moles into chromium atoms. And that happens with the ALO number. So let's take a look at this and see exactly how it works. Okay, here's the given right here. There's the molar mass right off the periodic table with grams on the bottom, so we can cancel grams of chromium top and bottom. Moles of chromium cancel moles of chromium, and what we have is atoms of chromium on the top. And now we're ready to finish off the calculation by, all that's left on the top is our 78 plus, or times the 10 to the 23rd. And on the bottom, all of the units are canceled out, so we have the number 52. And when you divide 52 into 78.3, it comes out to almost exactly 1.5 times 10 to the 23rd chromiums, which gives you answer D. In this question, they are asking you moles of chlorine. Now remember, no on 17. That's nitrogen, oxygen, or hydrogen. And everybody in column 17, which is fluorine, chlorine, bromine, iodine. All these guys are diatomic molecules, so we got to be careful of that. But they're trying to find the moles given the molecules. So a little time spent doing a diagram of what you're trying to do and where you're trying to go is very, very helpful. So these molecules are chlorine and the moles are chlorine. Now, It just so happens because we don't have to mess with grams, we don't need to worry about chlorine being monatomic or diatomic, but this is a good information to have for a question where you might be asked one of those. So what was my NOON 17? Nitrogen, oxygen, fluorine. Okay, nitrogen, no, NOH. Nitrogen, oxygen, hydrogen on 17. 17 is column 17 in the periodic chart. All of these guys are diatomic. Okay, so let's go down. Let's start with the given. Okay, and let's see how this guy works out. And no, let's do it this way. Okay. This little guy is our given, and that came from right here. We were given molecules, and we're trying to find moles, and we have to do that by using AVO, and AVO says 6.02, not 6.03. 6.02 times 10 to the 23rd molecules CO2 is going to be equal to 1 mole of CO2. Now, when I divide this 9.03 by 6.02, I come out with 1.5, and this 10 to the 23rd cancels this 10 to the 23rd. Molecules of Cl cancel. Oops, this isn't CO2, this is chlorine. And so molecules of Cl cancel. And what are we left with? Not CO2, Cl2, chlorine gas, and that is going to wind up being simply 1.5, and that's why your answer is going to be